Next Wednesday, the winners for the Nobel Prizes are going to be announced, and one chemist may discover that their name will soon be in a lot of headlines. Well, today we have gathered a panel to offer their opinions on who they think might be getting that call and why. It is my pleasure to introduce Jillian Buriak from the University of Alberta, Philip Ball, who is a freelance writer for Nature and a number of other publications, and Paul Bracher from St. Louis University. We will also be joined by Lauren Wolf and Matt Davenport from C&EN, who will be running the show today and getting your take on who the next winner will be. If you would like to share your opinion, you can use the questions panel. You can also join the discussion on Twitter by including @ACSWebinars and/or ChemNobel in your tweet. The slides for today's webinar can be accessed right now by clicking on the link that you see in your chat window, and the recording will be made available on C&EN's YouTube channel in the near future. And now, I'm pleased to turn the time over to Matt and Lauren to get today's presentation started.
All right, well, hello everyone. As I was introduced, my name is Lauren Wolf. I'm the head of science and technology here at Chemical and Engineering News, and I'm joined by my co-host today, Matt Davenport. Say hi, Matt.
Hey, everyone.
He's technically a physicist, but we've let him in the room today. We're claiming him as a chemist now. But really, the main event here are our panelists, and so they've been introduced, but I'll give you a little bit more background about each one of them. Paul Bracher is a professor at St. Louis University, but most people probably know Paul from his blog ChemBark. Paul has been part of this event in past years. This is our third annual one of these. Paul, I don't know, you can tell me, Paul, how many years you've put odds on your blog, but he's posted odds for who is going to win the Nobel Prize in past years.
I think this is the 10th year, something like that, maybe 9th.
So will we expect your odds? You haven't posted them yet, right?
I will. I'm going to post them after this. I want to give you guys the scoop, the sneak peek.
Sweet. That's awesome. Thank you. All right, so we have Paul. We've got Philip Ball. He's a freelance science writer, very, very well known in the science communication community. Phil has a background in physics and chemistry, has done a lot of writing for various publications, including Chemistry World, and oftentimes writes opinion pieces. So we're very excited to see what he has to say today. And last but not least, we've got Jillian Buriak. She's from the University of Alberta, and also she's an editor-in-chief at one of the ACS journals here. And last year, Jillian had her class watching along with the broadcast and asking questions, so we wanted to get her perspective this year. All right, and without further ado, let's get started. So moving on, before we get to the main event, I'm gonna tease the audience for a little bit longer. We're not going to get straight to the picks. I just wanted to talk about what it means to be a Nobel Prize winner before we get into that. And so, back in 1895, Alfred Nobel was writing his third and last will, and much to his family's dismay, I think, he left most of his money to the establishment of these prizes. And so basically what you see here on the screen are in his words, how he defined what a Nobel Prize winner would be. And you can see up there at the top, it's basically to be conferred to some work during, actually back at that time, it was supposed to have been done during the preceding year, but is being conferred to someone who's done work that's been of the greatest benefit to mankind. And so I don't think that holds true anymore, that it's only given for the work that was done in the previous year. I think the Nobel Committee has acknowledged that that's not true. They want to wait some time before they can see whether the work has had its greatest impact, and to even figure out exactly who to give the prize to, you have to see how long this goes on for before you can know really what the impact of the work is. Moving on, without further ado, my first question is to the panelists. Which chemistry laureate or prize over the years for you best exemplifies what it means to be a Nobel Prize winner? And we'll start with Phil.
Right. Well, that's a slightly different question. It's an interesting question because it's not asking us to say who's the all-time great. That would have been very tough. I've picked Gerhard Ertl. who won in 2007 for his work in surface catalysis, partly because he, to my mind, exemplifies the kind of winner that I'd like to see more often in the Nobel Prizes, which is someone who's really being, I think, rewarded for the lifetime's contribution that he's made. So this isn't a particular discovery. Gerhard never really made, a particular discovery that he's famous for. He's well known for a whole body of work. To my mind, this could get rid of this terrible disease that we now have of Nobelitis, of people chasing after the trendy discovery that they think is going to win them the prize. And I just feel that that's part of a competitive culture that's getting worse and worse in science and distorts the way things happen. I think that if the committee decided that they were going to wait and see who over their career has made a substantial contribution, that this would create a different atmosphere around these things. I think the idea, so often you see everyone going after a particular goal, or a whole bunch of people going after a particular goal. Whoever gets there first is often a matter of chance to some degree, or in any event, it doesn't particularly matter who gets there first because someone is going to do it right. Whereas I think the individuals who can contribute throughout a lifetime are ones who really we ought to be valuing and celebrating.
So Phil, it's really interesting because maybe an hour before the broadcast went live, there was a video that Chemistry World posted about whether the Nobel is ever awarded for lifetime achievement. They interviewed someone who used to be a former member of the Nobel Committee, and he was basically saying that it's not the way it works. Can you think of others? I mean, you sort of maintain that Gerhard got this for sort of not one particular thing, but a lifetime of work. Can you think of others who that's been true for?
I think there are quite a few. I mean, I think, for example, Ahmed Zewail got it for that reason, for a whole body of work. I think that some of the contributors, certainly to the prize for supramolecular chemistry, certainly Jean-Marie Lane got it for that reason. So, I think there's plenty of precedent for this happening. It's, I mean, it's interesting, the contrast with what Alfred Nobel set the prize up as at the beginning, but that was incredibly short term. I mean, so short term that, clearly, as you say, the committee had decided that's not going to work. We're not going to necessarily get the most important stuff if we just look over the past year. But I don't think necessarily you get the most important stuff if you, just go for the discovery that has made the most impact over the past 10 years. I think often it takes even longer before we really understand what contributions are most significant.
And Lauren, I think you see a number of examples of that in or at least recently. Martin Karplus's prize was probably considered a lifetime achievement. And then if you look at all the synthetic organic chemists that have won it, E.J. Corey, and then also R.B. Woodward, those are probably considered lifetime achievements where they made a number of syntheses. Robert Robinson. So it has happened, but it definitely is not. It's not the norm. It's the exception.
Yeah. All right. Well, let me pose that same question then back to you, Paul. Who is your chemistry laureate or prize over the year that best exemplifies the Nobel Prize?
Well, in the preview, so hopefully the next slide will come up, but I think that the two that really pop out at me are Rudy Marcus and Roald Hoffmann, kind of from opposite perspectives. When I think of the Nobel Prize winners, I think of people who just took a problem and killed it. And a super hard problem, or some cases just came up with something from scratch. So I'll start off with Roald Hoffmann. Back when people were looking at photochemical reactions versus thermal reactions in organic chemistry, they had no idea what was driving them one way or the other, and really it took Hoffmann and Woodward coming in there, and then Fukui as well, to kind of come up with a satisfying explanation that allowed you not only to explain what had happened, but predict new cases. And they completely revolutionized physical organic chemistry in that regard. And then after that, Hoffmann has been someone who's been on the scene who's not just known for his scientific discovery, which was huge, but has also served as a statesman of the field, where he's weighed in on controversial issues. He's dabbled or weighed in on politics. He's showed that chemists have a side besides being nerds in the lab. They could also be nerds in poetry and nerds as playwrights as well. So, I mean, Hoffman is just someone who is, now he's an elder statesman, but for his whole career he's been a statesman in the field, and it's massive. Rudy Marcus, when he came up with the theory of electron transfer in the 1950s, one of the most astounding things of it was a prediction of this inverted region for electron transfer, where there would be a point where there wouldn't, normally as things become more energetically favorable, they also become faster. But part of his theory predicted something that had never been seen, where something actually, as soon as it got too energetic, or as it kept on getting more energetically favorable, it would get slower. And that just blew people's minds. And we had to wait for 30 years for definitive experimental proof of that. But I mean, it just an amazing prediction, and one that came true. And it's someone, when I was at Caltech, Marcus is on the first floor of Noyes Building, and he's there like a Yoda figure, someone who's just like a Jedi Knight who you have nothing but the the deepest, most profound respect for. And when I think of a Nobel laureate, like the quintessential Nobel laureate, like Hoffman and Marcus, I mean, they're just impenetrable in terms of just. You cannot question their scientific merit. They are just incredible guys, statesmen in the field. And when I think of a Nobel laureate, those are the guys that I think of.
Those are good picks. Now, Jillian, we don't have a slide for you, so I'm just going to put you on the spot and ask you to answer the same question if you can.
So this was a difficult one for me because there are so many different flavors of Nobel laureates. So there are some people who do very fundamental work, and then there are other people who do a significant thing that can have a discovery, an enabling discovery that can have a dramatic effect. For instance, Bruce Merrifield, so Merrifield resin, solid phase peptide synthesis, which then led into DNA synthesis and being able to make these complex biomolecules via solid phase in high yields, and how that one important discovery led to so many different things. So that's an enabling discovery. But I'm going to go with something very fundamental, and that's Ahmed Zewail, who was mentioned earlier. I think Ahmed Zewail, who's known for femtosecond spectroscopy, really showed that the textbook examples of what we see as a transition state for a reaction are real. You can see them. They're not just kind of made up, oh, we think it's this. He was able to show that, and I think that had such a profound influence. It enables me as a teacher in the classroom to go in there and say, hey, not only was this anticipated or seen as a probable intermediate, but hey, you can see it. But there's also something interesting about Zewail that I think is really neat, is that he came from Egypt. His family had this dream of him going and doing a higher degree. No one in his family had a higher degree, and he succeeded in doing that. And I think that he's a real inspiration to so many people that you can come from anywhere and do really well in science, do great science. So he's my favorite.
And that might be a reason why he got the award by himself, and he wasn't acknowledged with anyone else too. All right. Well, let's move on. I'm gonna tease the audience for just a little bit longer, but I just want to give a tiny bit of background before we go to the main event of selecting this year's winners. Just to talk about how the Nobel Prize selection and nomination process works for those who might not know. These things go through the Royal Swedish Academy of Sciences, and so each prize has its own committee. And so what you're seeing here on the screen is this year's Nobel Chemistry Committee. I'm not going to even attempt to pronounce their names, but these are the folks who, they start in September actually for the following year, and they send out invitations, very exclusive invitations to people across the world to nominate people to win the prize for that year. And so these invitations go to people who have already won the prize in past years. They go to people who are members of the Royal Swedish Academy, and other people who are special by invitation, some other categories. And they take those nominees that they get back, and then they spend, it's a long drawn out process throughout the year where they vet them, they talk about them, and come October they eventually make their decisions. All right, so we're going to move to the main event now, which is the predictions. And we're going to start with Paul. If you were on this year's committee, which you can see there, who would you pick to win the Nobel Prize in Chemistry?
Well, I think that this year's prize is going to go to finally go to the bioinorganic chemists, the people who really created that field and who have, been the pioneers in that field. And the three that come to mind, because the limit's three, of course, are Harry Gray, Steve Lippard, and Dick Holm from Caltech, MIT, and Harvard. And this was a field that these guys created. It just wasn't there before they got on the scene. And Harry's been on the scene longer than longer than anyone else. He's generally, I think, credited with founding it. But what happened was that inorganic chemistry before that was relatively simple. I don't want to say relatively boring, but something where you just made complex. There were smaller complexes, small molecules, ligands made to that. These guys looked at metals that are involved in biology, and then all the sorts of things that could come of that. And they've each taken kind of different classes of it. I mean, Harry's looked at cytochrome, at the azurines. Lippard's got involved with a lot of proteins that are involved in neurochemistry and is considered kind of the father of inorganic neurochemistry, bioinorganic neurochemistry, however many prefixes you could throw in there. Dick Holm looked at iron-sulfur clusters and synthesized all sorts of mimics of those and kind of studied how those have been going on. And really, while you can't point to one thing that kind of was the knockdown, the knockout punch of all this, that they built from scratch a field that did not exist before and helped us understand how nature works and developed all sorts of probes associated with that. They've been on the radar forever, which is, I think, another important thing. Usually, I mean, it does happen. Sometimes things fly right under the radar, and no one ever saw someone winning the Nobel Prize in chemistry coming out of that. I think the quasi-crystals, to a certain extent, kind of, certainly people in the blogosphere kind of weren't looking that way. But usually when things come along, they've been on the radar for a long time, and they've been, they've survived the test of time, and everyone generally recognizes that these are very important discoveries, very important bodies of work, and this has just been on the radar forever, and it's time to clear it. It's, they deserve it. It'll be a richly deserved prize. Everyone agrees that this is, an incredibly important field, and that for the most part, these are the guys who were responsible for bringing it there. And I think this is the year that they do it. So I have them there as about 7-1 favorites for the odds there. So place your bets.
You heard it here first, folks. Paul will publish his full odds after this, but you heard his odds for this one here first. Paul, we're going to talk about the subfields that win in chemistry in a little while, but did that play into this at all, that inorganic hasn't gotten a prize for a little while?
To a certain extent. I generally look just to see that maybe back-to-back they haven't had it. So if the previous year was something that was more inorganic, then I think that wouldn't have been as likely. But generally after that, I kind of take it off. And for a while, especially for the prizes that are biology that tend to get shoehorned into the chemistry prize, I think that those I would tend to say you really don't want to stack those up, because then people really start complaining. But I don't think the Nobel Committee cares that much if we complain. In fact, maybe they like it more because it creates it creates a buzz, right? So there's no bad press, there's just press. And when people moan about biologists winning the chemistry prize, I think that they might like it. They're dirty in that regard.
All right. Well, let's move to Philip. Philip, who's your pick for this year?
Well, I took the question very literally, as I tend to do, because this isn't a prediction. I have to say that when you see the full list of everyone, and I've seen everyone else's predictions, and I think all of them are more likely to win than mine. But it's kind of for that reason that I wanted to nominate these guys. I wanted to nominate Mildred Dresselhaus and Sumio Iijima for carbon nanotubes. And The reason for that is that I think this is the part of carbon nanotechnology that has been overlooked, and yet, to my mind, it's the most important part. So I think it's absolutely right that, first of all, the discovery of fullerenes, C60 and others, was recognized in 1996. I think it's completely understandable that graphene took the physics prize in 2010. But in the middle of those two, carbon nanotubes are really, I think, what established this idea that there is such a thing as carbon nanostructures and carbon nanotechnology. Because they are the things that have really suggested applications, for one thing, but also they made the link, really, between graphite or graphene and these little molecules. They're an intermediate ground, and they, for a long time, they seem to be the basic building blocks of nanotechnology, the ideal sort of ready-made structures that you could use to assemble into nanotechnological structures. So they were first reported in 1991 by Iijima. He was working at the NEC Corporation at that stage, and he discovered them really coming from a background in microscopy, but in specifically microscopy of carbon fibers. And there's been a lot of discussion about whether this was actually a discovery or a rediscovery. There are, suggestions that they were seen in the earlier literature, and I think it's inevitable that they were, because, clearly they've been being made for a long time in the techniques that were used to make carbon fiber technology. But Iijima noticed what he'd seen. He saw them clearly enough to characterize them. He identified that they have this helical structure. So everything that is essential to carbon nanotubes was in Iijima's first paper. And then he went on 2 years later, he and independently, Don Bethune and colleagues at Almaden found ways to make nanotubes with just a single wall, and this was really important because this enabled us to really start characterize them properly as molecules, rather than these multi-walled structures that just had a mixture of different types of wall and had much more complicated properties. And it was Millie Dresselhaus who had explained why that was important, because she, along with her husband Jean and two Japanese collaborators, Ryuichiro Saito and Mitsutaki Fujita, published a paper that showed that single-walled nanotubes could have two different electronic structures depending on the precise arrangement of the carbon atoms. They could be semiconducting or they could be metallic. And those two properties, of course, opened up the whole possibility of using these electronic properties in nanoelectronics. And starting to make devices out of carbon nanotubes, and very quickly people started to do that. But I think that what was crucial at that time was that the realization that carbon could form these kinds of structures, these very precise nanoscale structures, then led on to the discovery of other structures like these sort of P-pod structures with things encapsulated inside nanotubes. You got stacked cups of nanotubes. You got these onion structures that were like sort of multi-layered giant fullerenes. All kinds of different morphologies of carbon that really gave rise to the idea that you could just do a kind of origami with these graphitic carbon sheets. And that's led in all kinds of directions. So carbon nanotubes, unlike fullerenes, carbon nanotubes really have started to find applications. And actually it's still early days for those, but already they're being used in composite materials for all kinds of things, from marine engineering to sports equipment, to baseball bats and hockey sticks. They're used as high-strength materials for yarns and sheets. People are starting to make macroscopic materials purely out of nanotubes. They're an experimental tool. You can stick them on the end of an atomic force microscope and get very high resolution images that way. They might be used as drug delivery devices if you stick drugs inside the tubes. They can be rods and actuators and rotors for making nanotechnological devices, and they can be used for electronics, and people are still taking this very seriously. IBM are still putting a lot of effort into finding ways of really getting nanotube devices to work as potentially the next generation of ultra small microelectronic devices. And for a long time it looked very uncertain whether this would work, but gradually people are stepping towards getting working devices this way, and there are people who think that this is going to be the next step when silicon reaches the end of the road, when we can't go any smaller. So, there are real applications for these things. I wanted to include Millie Dresselhaus not just because she did that important work in the field of nanotubes, but really for a body of work in graphitic carbon generally. It has been said, Faid Navoris at IBM has said that her early work on the electronic structure and the phonon structure of graphite pretty much told us all the basics that we needed to know when graphene came along. He said that a lot of her work is now being rediscovered in the field of graphene, and she's worked in so many other important areas too, particularly in developing thermoelectronic devices, which follows on from this work on looking at the interactions between phonon structure and electronic structure. So, in part, this is a sort of recognition for her of this tremendous lifetime achievement. So, I think it would be a shame if carbon nanotubes got overlooked and we sort of leapfrogged from fullerenes to graphite and then said, that's the job done, because they played a pivotal role in it all.
Mm-hmm. So for some of the reasons that you said, Phil, you were talking about how it's played into things with graphene and discoveries of phonons and things like that. Do you think that this particular prize for nanotubes might go to physics instead of chemistry?
Well, it could. Obviously, as I say, graphene did, although that prize for graphene was really not for the discovery of graphene. It was already known by that time. It was for the characterization of the physical properties of graphene and for realizing that it has these extremely important physical properties that make it an analog of all kinds of exotic physical, low-dimensional physical systems. So that was clearly in physics, even though graphene itself might find applications, more chemical applications as a material. But I think that carbon nanotubes really are chemistry. They're molecules, and it's the molecular properties that I think have characterized their importance. So it could go either way, but yeah, I think we should claim this one.
Okay. I'd love to see Millie win just on a personal level because she's such a lovely person. All right, well, let's get to Jillian's pick. Who, if you were on the committee this year, who would you pick?
I would definitely pick, it's a tough one, and I actually love Mildred Dresselhaus, and I learned inorganic chemistry from Dick Holm, and Harry Gray is just the most hilarious character ever in chemistry. I would love to see him win. But I really have to go with John Goodenough, and I have to go with John Goodenough for a few reasons. So he is an inorganic chemist, so that, of course, is a very solid reason. But he is the discoverer of the lithium-ion battery. And when you think about the lithium-ion battery and something that has had such a profound impact on humanity, on civilization, this thing is basically stuck to my hand, all the time. I don't know how many lithium-ion batteries I'm carrying around. The fact that in developing nations they were able to leapfrog, for instance, landlines, telephones, it all just went to this. And it was because the lithium-ion battery enabled you to be able to carry this power in a portable fashion anywhere, everywhere around the world. So John Goodenough was at Oxford University, where he was department chair of the inorganic division, and came up with the idea of lithium cobalt oxide cathode materials, which were then commercialized by Sony in 1991. And then he retired, but he retired at the University of Texas, Austin, where he then invented the iron phosphate battery cathode. incredible. This guy never stops. So he's 92 years old. Nobel Prizes are not given posthumously. I certainly hope that he's still research active, and I'm hoping for more discoveries to come from him, and certainly with the fact that his research is going full tilt, there probably will be. But I think it's time. I think this man deserves it, and he would probably share it with Stanley Whittingham.
Okay. And up on the slide here, you have sort of a close second if you want to
Yes.
talk about this one.
So completely unrelated. And this perhaps would be one of the lifetime type of awards that Phil was talking about, which is George Whiteside's, the most highly cited chemist alive. I guess it depends on who's doing the counting. Self-assembled monolayers, nanoscience on surfaces. How do you classify this person? Is he a chemist? Is he dabbles in biology? He dabbles in physics. Just is everywhere, and I just would love to see George Whitesides get it.
Yeah, one of my stories, my first year as a graduate student, I think just within the first month of joining my group, my advisor asked me to take him around campus for the day. He was there to give a speech and or give a talk, and she asked me to take him to all of his appointments, and I almost had a heart attack because I was like, what am I going to say to this man? You know, he was very gracious. We had great conversations, but also a very good pick. I'll give you a shout out, Jillian. I'm seeing some of the questions coming in from the webinar, and one of your, I think it must be one of your students, says that Jillian will clearly pick the right person because she's from the University of Alberta. So shout out to you.
Okay. Looking for extra marks.
All right. Well, you know, Matt and I are going to give our picks also, so I'm going to follow on to Jillian and give my pick because I also chose John Goodenough. You know, basically for all the reasons that Jillian said, and you know, I was reading an article in Quartz back in February about him, a really great narrative article about, you know, just without these lithium-ion batteries, where would we be, and the fact that, you know, people are using them in electric cars and trying to improve on them, and all of that stuff too. And I agree, it's not on my slide here, but I think he would probably get it with Stan Whittingham, who I believe was sort of the person who initiated the lithium-based concept in the battery. John made the sort of metal oxide cathode. And then I actually wondered, I did read, you know, when Sony went commercial with it in the 90s, there was a Japanese scientist, Akira Yoshino, who did this sort of carbon anode that sort of put it all together. So I don't know if you had considered whether he should be on there. I mean, we are allowed 3 for a prize, but it's you know, I just mentioned them all just in case, and then I can say I win if if they all get on there. All right. Well, so the question that we asked today was, you know, who would you pick if you were on the committee? But Paul also gave us an answer about who he thinks will win, rather than who he gave earlier, who he thought should win.
Yeah. Well, yeah. Just to clarify that, I actually think that if I were on the committee, that I'd actually go with Goodenough, because of I think that age definitely, you know, should factor into the decision to a certain extent. You know, it's a huge discovery, and you know, Goodenough is what, 93, something around there. Yeah. So, you know, the real tragedy of late that I always point to is Carl Djerassi, who was the father of the birth control pill, who passed away within the last year or so, and I think it's just an absolute travesty. It's a travesty that he didn't win it in either chemistry or medicine, one of them. For the contributions, him and others, for the contributions to that, to chemistry, which really had a phenomenal social change and impact on medicine as well. And there are a number of reasons that could have factored into that. But now it's a point that we can no longer argue because of prizes aren't awarded posthumously. But you know, lithium-ion batteries are absolutely huge, and it's chemistry, and it deserves a Nobel Prize. So, you know, given the time constraints involved, if I were on the committee myself, my vote would be for Goodenough too.
Yeah. I also, Paul, in talking about Djerassi, I think it's interesting, you know, the Nobel Prize Committee releases the nominations, basically, but they only release them for prizes from 50 years ago. And so we look through that database, and I think from 1965, you know, and earlier, Djerassi had only been nominated 3 times, but I suspect that once we get to start seeing the data in earlier times, I'd be really curious to see just how many times he was nominated without winning, and by whom.
Yeah. And he was someone, well, he had both a huge discovery and a wide breadth of work too. He was massive in terms of analytical chemistry and looking at using IR spectroscopy to identify organic structures and all sorts of, you know, like biosynthesis, like the precursors for these molecules were isolated from Mexican yams, and so kind of like doing semi-syntheses. He was all over the place, and he's one of those people like Hoffman who's just so richly involved in terms of culture as well. He was a playwright, he was an author. It's a shame.
Yeah. All right. In the interest of time, and we're going to speed this up, but I want to get Matt's pick, you know, first before we go further. Matt.
Moving on, yeah. I agreed with Philip. I went with carbon nanotubes and carbon nanoscience. So I think Philip outlined a lot of really, really good, really compelling reasons for this prize. Particularly, you know, having a physics background, I think being able to control the band structure of this thing that behaves like a one-dimensional conductor, a semiconductor, with just the position of the atoms is this really remarkable thing that people won't truly appreciate until we have a better handle on it, how to grow tubes either selectively or sort them once they're grown. So I think that's really cool. But I think my favorite and probably the worst reason I have is that, you know, physics has graphene, chemistry has fullerenes. We should just preempt this and settle the debate. Like carbon belongs to chemistry. We'll take it.
Chemistry. All right, yes, we've converted Matt from a physicist into a chemist. All right, and you know, real quickly, there were you know, as is the case for when you ask a scientist a question, sometimes they don't give you just one answer, they give you many. And so when I asked you guys this question in preparing for the webinar, you guys sent me some other options, and let's just go through these real quickly because we have some other questions to get to, and I want to open it up to the audience. We've already talked about George Whitesides and some of these other, you know, there are other people who could be named with him for self-assembled monolayers. I think that Jillian, you probably gave us a few of these other options that are on this slide. Did you happen to say Paul Alapisatos?
I suggested George Whitesides and a few others possibly, and Louis Bruce, and so Lou Bruce, Paul Levi-Satos, and Chad Merkin. I think Phil added Chad for semiconductor nanoparticles. Just they've had such a profound influence.
Mm-hmm. And I think Paul, were you the one who mentioned Bob Langer? I think.
I'm not sure, but I definitely think that he's up there. The question is, does he win a prize in chemistry or does he win it in medicine? Because a lot of the stuff he's developed have been polymers for drug delivery. But there's a huge breadth of work there. I mean, but you're looking at another fox character. You know, people talk about the fox and the hedgehog for Nobel Prizes, where Nobel Prizes typically go to hedgehogs, to people who focus on one problem and just nail it shut and have a huge impact in that one area. Bob Langer, George Whitesides, these are people who are foxes, people who have, you know, everywhere, big contributions, but to a lot of different things, and maybe not so much focus on one thing, and that seems to, over time, perhaps hurt their chances. So I don't want to say I'm not holding my breath for Bob Langer, or that it wouldn't be richly deserved, but I have him down on my odds list, not as high as some of the hedgehogs out there.
Yeah, and so at the bottom of this list, again, I think, Phil, you mentioned Jennifer Doudna and Emmanuel Sharpens here. I know a lot of people online have been sort of buzzing about them as contenders.
Yeah, and you know, I wouldn't be at all surprised to see them take it. Actually, the question here seems to be: is it too early? You know, I don't think there's any question. I don't think you can really argue that this technique has already transformed the way we do genetic manipulation. It's very clear whether or not it's going to be possible to use it safely in humans, may remain to be seen, but I don't think that should be the question on which an award like this should hinge. It's very clear that this is has really changed the game, and I don't see any reason why you should consider it too early for that reason. It may be that the fact that there's a patent dispute going on at the moment about this technique, that's going to muddy the waters, and that may be the thing that makes it that postpones this. But if this were to go to these two people for this discovery, I think that would be entirely justified.
Yeah. On a personal note, I think having two women win a chemistry prize in 1 year, it's a record for chemistry, and I would be proud for chemistry for doing that. And as you mentioned, the patent dispute, one of the questions that came in is, why is Feng Zhang from MIT not mentioned here? And so that person, of course, is who is involved in this patent dispute. So I think they probably need to figure that out maybe before this award is going to go forward. All right, so let's move on. We're going to poll the audience. We've given all of our picks. We have 5 options for the audience. We have Gray, Holm, and Lippard for bioinorganic chemistry, Millie Dresselhaus and Sumio Iijima for carbon nanotube discoveries. We've got Good Enough and perhaps some other folks for lithium-ion batteries. We've got Dudna and Charpentier for the CRISPR-Cas9 gene editing. And if you don't agree with us, there's the other category. You can type in your pick. If you don't see it on here into the question window, you can vote on the screen. And I'm going to close the poll very soon in 5, 4, 3, 2, 1. See what we got. Have 64% believe that Good Enough is going to win. And close behind that, a 17% for Gray, Holm, and Lippard. So let's see come Wednesday which one of those is right, or maybe none of them. As Paul mentioned, Dan Sheckman won a few years ago, and everybody said Sheckman who at the time. He was not on anyone's list. All right. Thanks for participating in that poll. We're going to move on to another quick question, and I'm sorry, I'm going to shamelessly plug the interactive graphic that C&EN released yesterday. But it brings a question. Every year, as we mentioned earlier, people complain. The award hasn't been given to a chemist; it's been given to biology, or there's biochemistry is taking too many of the awards. What about theoretical chemistry or some of the others? And so, in this interactive graphic, if you want to move to the next slide, what we did was we kind of broke down. You can see the entire timeline of prizes that have started from 1901 up until today, and you can see we've sort of visually depicted which awards went to which categories. Now, I have to admit that we did have to make a few decisions. We only represented 7 subfields of chemistry here. There were a few. I should say that we used the Nobel Committee's designations. They designate a category for each of these prizes. And for the most part, we used those. But there were a few where there was one prize in agricultural chemistry that, to make this readable, we made a decision about where to place that one in one of these 7 categories. But basically, the question I want to put to the panelists about this is when you look at these brackets of prizes, you kind of see that organic chemistry is sort of spread out over time, and physical chemistry is also spread out pretty equally over time. But the biochem has really just picked up increasingly since the 1960s. And so my question to you is, do you think that as time goes on, what it means to be a chemist is changing? And do you think that some of these categories might eventually not fall off of this graphic? They'll still be there, but they're not going to continue to get prizes, particularly something like nuclear chemistry. So let's start with Jillian.
So when I look at these I'm going to call them divisions in chemistry: analytical, nuclear, physical. In the research world, these divisions don't make a lot of sense anymore. We've been talking for years now about doing multidisciplinary chemistry, and whether or not we did it because we were told to. Actually, I think we just did it naturally. So these divisions really have become blurred. So if I bring up John Goodenough, what is he? Is he an inorganic physical materials chemist? You see what I mean? So these names to me almost don't make a lot of sense, because some of the more interesting work does come out of the areas that are between the traditional boundaries. So do these traditional areas even exist? Maybe that's a bit existential, but
No,
I
I thought about that in choosing good enough also. I thought, probably they would put him in the inorganic chemistry category, but we don't have a materials science category. So, all right, so I'll put the question to Phil. What do you think?
Well, I've found it very interesting, looking back over the list of laureates, to see that I think you really can see trends in chemistry coming and probably going. That in the early days, that's when all the, as you can see clearly here, where all the radiochemistry or the nuclear chemistry questions are, because that was what the questions were. What are atoms? What are they made of? Those are no longer issues, and so it's not at all surprising that those have fallen off the screen. There may still, I suppose, be space for a Nobel in synthetic elements. I'm not sure if that'll happen, but that's the area that's still going on there. But then you got into questions that were sort of broadly about the chemistry of stuff, particularly living stuff, about fermentation, as you say, agriculture, plant chemistry, hormones. Then this was in the 1930s and 40s. Then you got into questions of the early days of molecular biology. It became all about proteins, and so you had people like Sanger and Kendrew and Dorothy Hodgkin and Aaron Klug. So it was looking at specific biomolecular systems, particularly protein systems. Then you get into a much more sort of molecular scale biology, and you get people like Altman and Czech, Kerry Mullis, for techniques, Roger Kornberg. And so, at this stage, the kind of molecular chemistry of the cell is becoming understood, and we're looking in a more sort of holistic way rather than at individual proteins. And recently, I find it hard to see any trend. It just seems to have become much more diverse. That you still, as you say, have got awards in physical chemistry. You get awards in techniques, like last year's award. There are obviously still regularly these contributions to molecular biology coming through, but also to inorganic, like for example the Shechtman Award. So it's at the moment it's much harder to see any trend over the last sort of 20 years or so of what's hot. But I think that looking back broadly historically, you do see a progression that I think reflects the increasing depth at which we've understood chemical systems in the broader sense, so that we've really started to see living systems in their molecular terms. We've pretty much agreed that we understand the fundamentals, I suppose, of chemical bonding and of atoms themselves. So I think it's going to be very interesting, in 20 or 30 years' time, to look back, and we'll be able to see what this era is all about. Will it have been about nanochemistry and complex molecular systems? Will it be about being able to see the dynamics of chemical systems in much greater detail? Don't think we know yet, but it'll be fascinating to find out.
Okay. Let's go to Paul. Paul, we're going to do one more poll question after you, and then open it up to the Q&A.
All right. I mean, I'll be quick. I agree with what Phil said and a lot of what Jillian said in terms of these names are archaic. I mean, for the most part, you classify yourself now, whether you're an organic or inorganic or physical chemist, based on what you teach, not what research you do. So it kind of doesn't matter. And if you kind of look at probably what happened with some of these things too is that Nobel didn't even, back in the 1900s, the turn of the century, people weren't even thinking about all the possible discoveries in biology that were enabled by the chemistry that came in the 50 years after it. So he made no Nobel Prize in biology, and that kind of has been shoehorned into chemistry. But these divisions that have existed in the past, they're just not there anymore, and new fields are opening, other ones are closing, and it's all blending together, and it helps to try to organize it, but really it's you can't do anything in a satisfying manner. So it's kind of it's fun but silly to worry about it.
Well, with that, we're going to have a little bit of silliness then with this next poll from the audience. We're just going to ask you out there, which subfield do you think is going to win this year? We've got biochem, we've got organic, we've got physical, inorganic, theoretical, and I'll say sorry to the nuclear and analytical fans, we couldn't fit them on here. But please go ahead and vote, and I'm going to close the poll in 5, 4, 3, 2, and 1. We have inorganic, 44%. Inorganic's getting a little bit of love this year, and biochem is going to go after, is second after that, followed by pchem. All right, thanks everybody for participating in that. We're gonna stop there and open it back up for the Q&As, but before we do that, I'm going to hand it back over to Mike.
Thank you so much. I just wanted to let you know what was coming up in next week's webinar. So make sure to join us next week for a special interactive webinar. We'll be featuring Rich Hartel, who's going to be joining us to cover the chemistry of gummies, caramels, jellies, and candy corn. So if you've ever been wondering what's really in candy corn, he's going to let you know. He's also prepared a list of candies that you can have on hand to make the webinar a little bit more tasty. Then come back the week after that for a look into the chemistry of pigments and the different materials that artists have been using over the centuries to bring color to their artwork. So after, we'll just throw it back to you two to get started with this question and answer session.
Great, thanks, Mike. So I am actually going to stop and let Matt, my co-host, handle the Q&A. He's been monitoring the Twitter feed and the questions that are coming in on the webinar. And over to you, Matt.
Yeah, that was a fascinating discussion. If you guys have a chance to check out some of the comments that came in, please do. A lot of good feedback from all over the world. I am now tasked with picking out the best questions, which will be really tough because a lot of good stuff. I guess to follow up on that last sort of discussion we had, where I think the consensus is that the subdivisions, at least that we've put forth in our infographic, aren't entirely useful. Maybe another interesting take on that, a similar question is, what's the criteria that separates the chemistry prize from the medicine and physiology prize?
Well, I mean, I just think that it's whatever the Nobel Committee wants, whatever they feel like. I don't think it's worth trying to make sense of it because it's what those 5 or 6 people feel like, and you just have to sit there and take it. So a lot of people get all offended that, you know, biology stole our prize, but the Nobel Prize is, whoever deserves the Nobel Prize is whoever those 5 people think, and that's just the way it is. So I don't think it's productive too much to worry about that because of it's a private thing. It's not. This isn't a democratic process, and it's just something to have fun with. So. It'd be interesting to know if they had any internal guidelines for, like, hey, don't step on our toes over here. That's ours, not yours. But I don't think we'll ever get a satisfactory answer to that.
So I'll try not to cough up a fur ball with that one, but no, I think perhaps we can also quote that Supreme Court Justice of the U.S. I know it when I see it, and I think oftentimes it's chemistry when you see it. It's just your gut instinct.
I think there's always been an element of arbitrariness to this. It seems to me that the Watson and Crick Prize should really have been in chemistry. I see no reason, why that was singled out when so much else of molecular biology was what we now see as molecular biology was being awarded in chemistry, and I think rightly so. So actually, I know there is, that every time this happens that a biologically tinted prize gets awarded in chemistry, there is some complaining about it. I think chemistry ought to be proud of claiming those and should be claiming probably more of them than it is already.
Yeah.
All right, we're running out of time, so I'm just going to direct these last couple questions to individual members, and then we'll come back for a final wrap-up where you can all weigh in. Jillian, this question came in during when you mentioned whitesides. Do you think, so one of the things that, I'll just ask it, how close is he to winning the Nobel Prize, and is this the closest, is now his time, or do you think it's been closer in previous years? I'll let you handle that.
So George Whitesides is an enormous figure in chemistry, but he's also an approachable figure. And the last few years, just around this time, I'll just send him a quick email and say, I really hope you get it this year, George. I think he's been in the running for at least a decade. That's my impression, but he's, as we said before, he's had an influence on so many areas, but I'll single out self-assembled monolayers, which has become the basis for a lot of chemistry of surfaces, gene chips, etc. So I'd say for over a decade at least.
All right, this one's for Philip, because I know you've got a little bit of a physics background. Are you surprised that this year we didn't have much discussion about Nobel Prizes for photovoltaics?
Oh, well, because of course Michael Gretzel has been a very popular prediction for several years, and I think, you know, with very good motivation. I wonder whether part of that is that still the technology that he developed of nanocrystal solar cells has it's taken a long time to get to something commercial, and you know, it's still only just sort of starting to get there now. I mean, I visited Michael, blimey, about 4 or 5 years ago, and you know, at that stage he was saying we're almost there. But I guess my feeling is that if that's the reason that that the committee is holding back, you know, I'm never very happy with this idea that we have to wait until something is completely verified or until something is in the marketplace before the prize is awarded, because it seems to me that what's really important in science is that you have an idea that's productive, even actually if it isn't completely right. If it's productive, if it gives rise to a lot of activity in a field, then that's really what's important for science. And you know, Michael's idea clearly has done that. There's been a huge amount of interest, not just in the particular systems that he developed, but in finding completely new kinds of system like this that will be able to make use of solar energy. So, you know, were that to happen, I think it would be entirely justified.
Yeah, agreed.
I think that, just to weigh in there, I think that
final. Yeah.
Just 1 sentence. I think that you're not going to see a whole lot of you're not going to see a prize for solar energy until solar energy is solved, and dye-sensitized solar cells aren't the solution that's going to provide consumable energy for the masses. I think that the committee's going to wait for that.
All right. So, Lauren, do you want to wrap it up as we are closing in on the hour mark?
Yeah, let's. Thanks to everyone out there for all the questions. We're sorry we didn't get to all of them, but I'm going to ask a last wrap-up question. After all the conversation that we've had today to our 3 panelists, very quickly, did anything we said today change your pick? Jillian.
I've always thought Gretzel had it. I do think Gretzel et al., and I don't know who et al. is. Yeah. We only had space for 2. I would have picked Gretzel as 3.
All right, Phil.
Well, you know, I have to admit that I do share people's view that John Goodenough kind of should win it. I wanted to take the opportunity to nominate my 2 guys, Iajima and Dresselhaus, because I don't think anyone else was going to, and I just want to have their names there. But I think that the arguments that have been made for why John Goodenough should win are very, very compelling.
I will say it was funny because Matt and I had talked about his picks, and then you sent me yours the very next day, and he said, I don't think anybody will pick this either, so it was very interesting that you both did pick them. All right, Paul.
No, I mean, I think that any of the people mentioned would be great winners. I'm pulling for Goodenough for the reasons mentioned before. I think the bioinorganic people will win eventually, and this might be their year too. So we'll wait and see.
You will.
All right. Well, thank you so much to our wonderful panelists and cats, and thank you to my co-host Matt. And I'm just gonna kick it back over to Mike real quick.
All right. I'd like to thank everyone in the audience for tuning in, including Rashid, who said in his own words about a previous webinar that we've had. I'd like to thank you for organizing all the webinars, especially today's ACS webinar that had a big impact on my students regarding safety in organic chemistry laboratories. This will really enhance their interest in working in organic chemistry laboratories and engage them in real research project-related green chemistry. Now, if you have a topic that you would like to learn more about, let us know. You can reach out to us through Facebook and Twitter, or by email at acswebinars@acs.org.